Okay, so we were discussing this paper and we were able to cover half of these slides, and we said, okay, the remaining part we can talk about uh, in this lecture. So the paper was about the name of the paper is not row hammer, but this phenomena is known as row hammer, where basically what is done is that a malicious person can repeatedly uh, open and close the same row of the memory array. And as a result of repeatedly opening and closing the same row, it can actually induce errors in the neighboring rows. So last time we talked about the last slide we saw was like, okay, they tested various memory modules and memory chips from different manufacturers, and then they show, okay, how much number of errors they can induce in each memory module from the memory modules from each manufacturer. And they saw that, okay, these errors because of row hammer, they started appearing in memory modules after starting from 2010 onwards. And okay, so here they are defining in this slide, they are defining error. So error is basically the charge loss. So if there are two types of errors, so remember we talked about noise margin, right? Noise margin high and noise margin low. So one error is when you have the logical value of bit from 1 and it flips to 0, and the other is reverse of it when you have the logical value of the bit 0 and it flips to 1. Okay, so a given cell will definitely, it can suffer only from one of these two errors, from 1 to 0, depending upon its value, because at a given time, a cell can have only one value, either 1 or 0. So the error it can suffer is only also 1. So there are two types of cells, one which are known as true cells and the others which are known as anti-cells. So true cells are those which use the high voltage level to indicate the logic 1. Okay. And anti-cells are those which use the high voltage level to indicate the logic value of 0. So they are known as anti-cells. Okay. So which memory modules use which type of memory cells, it depends upon the manufacturers, or it is their choice. So why this is important? Because the number of errors or the behavior of the errors they observe, it basically depends upon the type of the cells used in those memory modules. That's why they want to first just explain it. That what are the true memory cells and what are the anti-memory cells. So true cells, they have error only when there is a logical change from 1 to 0, because there is a voltage discharge, because this is high voltage and this is low voltage, right? And anti-cells, they have error only when a bit flips from 0 to 1, because bit 0 is high voltage and bit 1 is low voltage. And voltage when a discharge happens, it only happens when the current flows from the high voltage to the low voltage point, right? So errors are manifestations of the charge loss. So if you have something, then you can lose it. So you high voltage, then you can lose that as a result of the current flow. So one thing they wanted to study was like, yes, they said, okay, if we repeatedly keep opening and closing the same row, we can induce the errors. And the row which is repeatedly open and closed is named as aggressor, and those which have errors induced in them is named as victim rows. So they wanted to study that, okay, what is the relationship between the aggressor and the victim rows? Both rows and the cells. So what is the relationship between an aggressor row and the victim cells? And what is the relationship between the aggressor row and the victim rows? Okay. So what they found is like these are like the blue, orange, and green. These actually indicate the memory modules from 3 different manufacturers, and they pick those memory modules from each manufacturer which have highest numbers of errors in their previous experiment and are in the previous table. So they are naming it as worst memory chip from manufacturer A, B, and C. Okay, so what they did is that they did an experiment where they record during each test they record the address of the aggressor row and also the address of the victim row. And then they take the difference between their address, right? And then they find, okay, how far, like if address and victim row is the same row, then definitely there is difference of address of 0, right? But if they are adjacent to each other, then there is a difference of 1. And if they are like not adjacent but next to each other, like there is a gap of 1 row between them, then it is 2 and so on. So here they are showing on the x-axis that what is the distance between aggressor row and the victim row. So 0 mean no distance, 1 is mean 1 and -1 mean at next immediate neighbor. And then 2 and -2 mean that neighbor after skipping 1 row. Okay. So what they found is like they found the highest number of errors are induced by an aggressor row into its immediate neighboring rows on both sides, like at a display side, like on, let's say, +1 and -1 side. And very few errors are induced in the rows which are at a higher distance on both sides. So most aggressor and victim rows are adjacent. Actually, this is also a very good example of how to prepare the slides, right? I mean, they are not going into like nitty-gritty details of the paper. They are giving you the higher level lessons learned from the paper, right? But even they are like very specific and informative at the same time without going into deeper details because they are available in the paper. Okay, so then yes, they found out, okay, this is number of the errors we can find in each memory module as a result of row hammering. And okay, this is the relationship between the aggressor row and the victim row. But then they wanted to perform some sensitivity studies. What kind of sensitivity? So in sensitivity studies, what you normally do is like, if you have a system with multiple parameters or multiple variables, so what you do is like, you keep all other parameters or variable fixed, and you change the value of one particular parameter in a range. And then you see that how it affects, let's say, the performance of the system, or how it, in this case, how it affects the number of the errors which are induced. Okay, so they are going to do this in this sensitivity study. So what they do is like, first they explain that how they are running their test. So they are first running their test on row 0, then they are testing row 1, they are testing row 2. So remember, we said that memory is nothing but an array of cells, right? So a two-dimensional matrix. So you are first testing the row 0, then row 1, row 2, row 3, and so on, until you test all the rows in your memory module. Then when you are in each particular test, what you are doing is that you first fill the memory module with data, with the data, and then you repeatedly open and close that particular row. Let's say the row 1. And in the meantime, when you are doing repeatedly opening and closing, you are also doing the refreshing your memory periodically. Actually, I don't know whether you were able to go through the background slides or not, but in SRAM, static RAM, what happens is like no, not SRAM, DRAM, sorry. In DRAM, what happens is like you have this capacitor, which is used to store the charge. And then this capacitor is connected with a switch, which is a transistor. Okay. So what happens is like if you apply the high voltage, and let's say you have stored here 5 volt, right, which is logic 1. So if you apply the high voltage, then current will start flowing from this from source to drain, and you will see here a high voltage available, so which you will interpret as logic 1. Okay. And if it was, let's say, if it was not 5 volt, but it was 0 volt, and you can connect it here, you apply the high voltage, which basically means you turn the transistor on. So you will again here see the logic 0. So this is how it works, right? Now, the issue with this capacitor is, like, let's say if you have stored the logic 1, high voltage, the issue with this capacitor is like it leaks the current in this direction. So that the amount of that leakage current is small, but over the time, if you don't recharge the capacitor, what happens that all of its voltage will be there will be a time point when all of its voltage will be discharged and you will be left here with zero. So what happened that you actually stored logic 1, but if you never recharge the capacitor, there will be a time when you will read the data and it will turn out to be zero. So which means your data will be lost. Your data will be not reliable. So what you need to do is that after a certain amount of time, you have to recharge the capacitor, which is known as refreshing the memory. Okay. So there is a time period which is now typically 64 milliseconds for DRAM that you have to refresh all the cells of the memory in every 64 after every 64 milliseconds. Each cell must be recharged once in each 64 millisecond period. Okay. So what they are doing is that when they are like repeatedly opening and closing that particular row, at the same time, you are refreshing the memory periodically, right? For example, after every 64 millisecond, all the charges are in 164 millisecond. After every 164 millisecond period, all the cells will be recharged. And then after doing that, like repeatedly opening and closing this particular row, after that, they will find errors in the module. So this is how they are performing their test. Okay. And how they are repeatedly opening and closing the particular row. We have seen that example snippet code in the previous lecture. Okay, so what now they are going to perform the sensitivity study. So what parameters? So there are like 3 parameters which they are which they want to for which they want to perform the sensitivity study. One is access interval. Access interval is, remember we talked about the word line. So if you have an array of, let's say this is your array of cells, and you have this word line signal. So if you activate it, what happens that all the data of all the row will become available in the row buffer, right? Remember from the previous lecture. So, but there is a time limit. So like how frequently I can activate and deactivate this write lines word line signal. Okay. So like let's say if I activate it at time 0, then is there any time limit or time period for which I have to wait before I can activate it again? Okay. So there is a time period basically, which is known as activation interval. So what is the time difference between 2 activations for the same word line? Okay. So the default is 55 nanoseconds, minimum is 55 nanoseconds. So what they did is they performed the sensitivity study where they changed it from 55 nanoseconds to 500 nanoseconds. Okay. The second parameter is refresh interval. Remember we said we need to periodically refresh the DRAM, all the cells of it. So how frequently we can, how frequently you refresh? So they changed that refresh interval in the range of 8 to 128 milliseconds. Okay. And third thing which they test is like, remember they first fill the memory module with data. So what data you write in the memory? So they tested with different memory patterns. One is that where they are write all ones, all zeros, or they have what is this stripe pattern where like I think all the even rows are written zeros and all the even rows are written 1 and all the odd rows are written with the value of zeros. And also another pattern which is like inverse of row stripe. Okay, inverse of row stripe mean like you write all the even rows with zeros and all the odd rows with ones. Okay, now let's have a look at the result of the sensitivity study when they keep all other parameters same and they only change the access interval in their experiment. Activation interval. Actually, they are not consistent with using the term because in the paper they are saying activation interval and here they are saying access interval. Okay. So in this figure on the right, on the x-axis, you have you are changing the access interval, like what is the time difference between 2 activations of the word line for the same word line. Okay, so you are changing it from 0 to 500, and on the y-axis you are indicating that how many errors were induced for that particular value of the access interval. So you cannot have an access interval smaller than 55 nanoseconds. So this is the lowest possible value which is allowed in the memory modules. And this is what they observed. So before we talk about the line, so here if you are increasing the access interval, it means that you are activating activating the line less frequently, right? Because you are increasing the interval. And if you are reducing the interval, it means you are activating the line more frequently on the left side as you go to the left. So what they have, first thing what they have observed is that in the memory modules, in the bus memory modules from all the manufacturers, you observe the same pattern, which basically is like as you increase the access interval, as you increase the access interval, your number of errors start reducing. So if you are increasing access interval, it means that there is more time difference between two activations of the same word line. So you are activating it less frequently, which means you are charging and discharging it less frequently, right? So as a result, remember that coupling effect, which we said, it depends upon how much electrical activity you are going to have in your transistors. So lower the amount of activity you have, lower the electromagnetic effect and coupling effect you have, and as a result, a lower number of errors are induced. So here we see that as the increase, as the lower the frequency of the access are activating the word lines, the errors which are induced, total number of errors which are induced in the memory module, they are also reduced. Until there comes a point where the errors induced reaches zero. Here. So the key takeaway is that less frequent access leads to fewer errors. Okay, in the second study, they are going to, by the way, you can stop me or ask me the questions. So I don't want you to put the dummy questions in class participation form. Okay, I want you to be like involved. So second parameter they change is like refresh interval. So now they are keeping these two things same, access pattern and the activation interval. So this is like the typical refresh interval. Actually not typical, it is required in the paper. They said that it is required that for all the DRAM modules, your refresh cycle should be greater than or equal to 64 milliseconds. Okay, so they did the experiment on the x-axis. What they have is on the x-axis they have like the range of the refresh interval from 0 to 128, and on the y-axis they are reporting what is the total number of errors they were able to induce in each memory module from bus memory module from each manufacturer. So one thing, one thing again is like the pattern is same across all that. Yes, the absolute values are different, but the behavior is same, which is basically that as you increase the refresh cycle, refresh period, or refresh interval, your total number of errors which you induce, they start increasing. Why? Because increasing the refresh time of the refresh interval increasing means that you give more time before this capacitor is recharged, right? So if you are like, let's say if you are recharging after every 64 millisecond and then you increase it to 128 millisecond, so there is you cannot like reinforce it, or you cannot recharge it back to its original value. And in this case, what will happen that you will be more susceptible to errors which are induced as a result of opening and closing of the aggressor row. Yes.
So on the other graph for the access one, it had a plot that was like blocked
Previous one
out.
we were talking about?
Yeah, there was a plot that was blocked out, probably for security reasons, so that way they wouldn't be accessing it too fast. Why, that part is like not allowed there. Why on this other graph, the second graph, why is there nothing that they blocked off there? It's like at 65 or 64 milliseconds.
because your all the memory modules they tested, they don't allow to have an
Yeah. I'm talking
lesser
about-
than that.
So that one has the part that's blocked, but
Yeah.
on the next graph, it doesn't have anything.
Yeah.
Blocked up. If the error is kind of at 64 milliseconds where they kind of start being like,
No, this is
why is there
like
nothing blocked off?
yeah. So that's like a valid question. I mean, in the paper, they say that our DRAM modules, they require at least greater than or equal to 64 millisecond. Now, the question is like how they were able to conduct the experiment if the memory module was, and I'm not sure. Maybe they had some, I don't know, some kind of access where they were able to do it because they were doing this project with the Intel. So maybe they had some kind of mechanism which was not public. I'm not sure. I'm not sure. Let me finish this graph. Okay. So in all cases, what they see that as you increase the refresh interval, your total number of errors in each chip module increases. And the other thing what they noted is like if you want to achieve zero errors, the zero errors are induced, then you have to achieve a refresh cycle close to like in the vicinity of 16 milliseconds, which means you need to refresh more frequently, which basically mean you will be consuming more power because refreshing, and not only more power, you will be consuming more time. You will be incurring more latency overhead because when you are doing the refresh operation at that time, you cannot read or write data from the cell. So which is like, it will make your memory module not available relatively for more amount of time for any read or write operation.
How's the refreshing operation different from the accessing one? What are they for, or
Okay.
how they relate?
Okay. So let me first explain how reading or writing, let's say how reading happens, okay? And then I will explain how write, like at a very high level. So let's say you have this, again, this an array of cells. And then definitely there are other rows, okay? I'm not drawing them here. So let's say you provide an address, and based on your address, this particular word line is activated, okay? So what happens is like, actually in the background slides, I have a schematic diagram from Dr. Onur Mutlu. And you can go there and look what is like low level diagram of things, how it works. So basically what will happen that when this word line is activated, so the data stored in this bit, let's say, let me put some dummy values, 1 0 1 1 0. So it will be placed on the output line, which are known as bit lines, okay? So these are bit lines, okay? So this is bit line, this is bit line, and so on, okay? And then it will be lashed into the, or it will be then this, whatever voltage is placed here, it will be sensed by a sensor, which will interpret it as a logic 1 or 0, whatever, and place it in the row buffer, okay? But that is not the only thing when it is not the only thing happening during the read operation. In the read operation, the data is read from the row and placed in the row buffer. And after placing in the row buffer, it is also again written back, same data is written back in the same row, Why? Just to refresh these. Oh, I erased it. Just to refresh that that capacitor, which is actually holding that data, right? Because when you read the data from the capacitor, you remember, you have this switch. This is output. So current flows here. If current flows, then it will be discharged, right? But you are reading and you want the data to be retained there, right? For future reads, let's say. So that's why what you do is you write it back, okay? So this is how read operation works. And in refresh or read or write. In refresh, what happens is like you actually do the same thing. You open a row, simply open a row, brings the data into the row buffer and put it back, irrespective of whether a read request is made for that row or not, right? But you make, so basically refresh is incorporated in a read or write operation itself. But if, let's say, a row is never requested to be read or written, you still need to refresh it, right? Otherwise, it will lose data over time because of the leakage current. So what happens that you simply bring, let's say this row is never requested to for a read or write operation. So what you will do is that you will bring all of its data into the row buffer, then put it back, then next row, then next row, next row, so on. And in 64 millisecond, you must complete refreshing all the rows in your memory model.
Not just to keep them active, right?
Just to keep the data, just to retain the data. Otherwise, because of this leakage current which flows in this direction, and here this is ground, let's say, because of this leakage current, your data will be lost. Okay. Okay, so what here again, the same thing, if you want to achieve an error rate of 0, or number of errors to 0, you must perform 7 times more frequent refresh operations. Okay, more frequently. Just give me 1 minute. So more frequent refreshes will result in fewer errors. Yes, go ahead.
I was going to ask, how does the leakage affect the losing data?
Again, so, okay, I am not an electrical engineer, but in our bachelor's, we have taken the course on digital electronics and analog electronics. So here is the basic thing which I remember is you have this capacitor, and even as I explained earlier, it is connected with a transistor, right? So if you apply the high voltage on the gate, this is known as gate input. If you apply the high voltage in the gate input, what happens that effectively, this is known as channel. What happens is that this channel starts conducting the current. So this is the source and this is the drain, right? But if you apply the low, this is when you apply high voltage. But if you apply low voltage, then actually what happens that there are no carriers, charge carriers in the channel, and no current can flow, right? So let's say if you had charged it initially to 5 volt. So if you apply high voltage, current will start flowing this direction. But let's say if you apply low voltage, right? So no current can flow from here. So effectively these two are disconnected, and you expect to have 5 volt to be available here for ideally. You want it to be available for infinite time, right? But that is not the case. Why it is not the case? Because current does not only flow in this direction when your gate is conducting, but when your gate is conducting or not conducting, irrespective of that, your current, a small amount of current also flows in this direction. Okay, and this is known as leakage current. Though the amount of this current is very small, but it is not 0. And as a result of that, after a certain amount of time, depending upon what is the amount of leakage current, your capacitor will get discharged completely. So if you had the 5 volt, which is logic 1, it will not be logic 1 after a certain amount of time, it will be logic 0. You will not be able to retain your data. Okay.
It retains for 64 milliseconds.
Yes. Yes.
Why is it 64?
Because it depends upon your physical and electrical properties of the capacitor, which I don't know and which I cannot discuss it. Okay. Yeah. Okay, yeah. Okay. Let me just cover this last thing. So the third parameter for which they perform the sensitivity study is data patterns. So they tested different data patterns, solid and row stripe here, for example. But what they observed is that for this particular row pattern, data pattern, they observed 10 times more error as compared to all ones and all zeros. So basically, it tells you that the number of errors which are induced, it is affected by the data stored in other cells, not only the cell in which you are inducing the error, but it is also has some kind of relationship with the data stored in the other side. Okay, so I am not going through the naive solutions. The last solution, actually they listed 6 different solutions as a naive solutions, and then they talk about one solution which they think is like low cost and low performance overhead, which they are naming as para probabilistic. Para what? Para stands for what? Okay, probabilistic adjacent row activation. So basically what they do is like whenever a row is activated and after that it is closed. So upon closing any row, what they do is like they refresh. Remember in the previous slide, if you increase the refresh frequency, or which basically means decrease the refresh interval, then you can decrease the number of errors. So what they suggest is that whenever any row is closed, so you refresh its adjacent rows on both sides, one of the adjacent rows on both sides with a low probability. So basically they say that you have a coin, bias coin, like which has, let's say, a high probability of head and low probability of tail. Like let's say the high total probability is, let's say 1. So high probability of, let's say, head is 95% and probability of tail is 5% or 0.05. So what they say is that whenever you close a row, you toss that coin, and if it turns out to be, let's say, tail, which has maximum probability of 5, so what you do that one of those two adjacent, it looks like I'm moving my hand in air. So you have this aggressor row, and let's say this is your victim row on one side and the victim row on the other side. Let's say victim row 1 and 2, right? So whenever you close it, you toss a coin, which has like, which is a bias coin, which has tail probability of, let's say, 0.05. So if it turns out to be tail, then what you do is like you refresh one of those neighboring or victim, let's not say victim, but neighboring rows. So, and you can select randomly, like with 50% probability row 1 and 50% probability row 2, okay? The advantage of this scheme is like you don't need to maintain any information, like any metadata, like last time which row was I have refreshed, which one of the neighboring row I have refreshed. You don't need to maintain it. You don't need any extra hardware support. You don't need any, you definitely need to change some changes in your system software to enable to refresh these rows, and it has low performance overhead, okay? And it results in there are no, like they are not able to achieve the 0 errors, but still they are able to achieve a very low number of errors as a result of this approach, okay? Any questions?
Real fast. So I know it's a low probability of it switching the other ones, but if for some reason there was like, they just decided to like all switch every time, could this not make like more of an effect, like waterfall out, so you could have more rows possibly, like rows?
You can have more what?
So like rows further away might get damaged if for some reason, like, so you have this one that's going a lot, and then these ones see that and they're refreshing, and then that's making this one refresh a lot. If like the chances just, it happens to be going every time, then wouldn't that make it so maybe like,
You are saying that
like
if this
VR6
refreshed,
like VR6 could get hit by the row hammer if for some reason the coin flip made it so that way, like every time that one AR went, VR2 would also flip, which then make VR3 flip if the chances just hit like that. So it's a low chance,
It's
but
not
could
recursive, is it? It's recursive.
like, so yeah, would, if the one in the middle there is going a lot, and then it makes VR2 also go a lot.
do
Could
to
it-
refresh?
Yeah, to refresh, would it make it so VR3 would also refresh, or would it just?
No,
not?
it will only refresh the neighboring row, not the VR3.
But if VR2 is also refreshing, that wouldn't trigger VR3.
You mean it
to
will it not
refresh,
induce
'cause
error in VR3?
VR3 would see that it's opening a
Yes,
lot.
it's not recursive.
Okay,
No.
so could it then cause damage to VR3?
No, because if you are closing as a result of, when you say, keep in mind your attacker. What is attacker doing? Attacker is repeatedly reading from the same row. Okay, two different rows, X and Y, X and Y, now refreshing them. So when you observe that, okay, any row is closed, you refresh its neighbors. So now refreshing is different than
Oh, okay.
reading and write.
So it wouldn't have as much, like the same effect on.
No.
those.
No, and also as a part of refresh, whenever you refresh, you recharge the cell to original value, whether it was 1 or 0. Okay. Okay. Let's stop here, and I need to rush.